Okay guys, in this video I wanted to go over some strategies for optimizing molecules using Gauss view on the Macintosh computers in the numerical lab. And so here I've got Gauss view open, and as a test molecule what I'm going to do, I'm going to make a new molecule group here. So I've got a molecule I can work with, and what I'm going to do is I'm going to do aniline. So I'm going to start with the benzene ring here. I'll go ahead and center that up. And then I'm going to add this nitrogen tetravalent substituent. You can put it anywhere you want, really. It doesn't matter that much. And so this is aniline. So this is the default structure that Gaussian Gauss view builds for us. And so what I'm going to do is just a quick semi-empirical optimization of this molecule. And this is often something that you might want to do because they're short, quick calculations, and then they will give you a reasonable structure, starting structure for most molecules. So I'm going to go to the calculate menu item, run the Gaussian calculation setup, and so I'm going to select for my job type optimization frequency. I'm going to just use the default settings here. So optimize to a minimum. For the method, rather than doing an ab initio method or a DFT method, I'm going to choose the semi-empirical using the PM6 model. Changed on me. I'll use PM6 here. It's a good, robust model. And so for my job title, this is just an initial optimization plus frequency job for aniline, and we're going to see what we get out of this. So I'm just going to submit that, save the input file. I'm just going to call it aniline. Save that, and it won't take hardly any time at all to run. I'm going to close the input file, and the output is going to pop up in just a second. Like I said, these PM6 jobs run really fast, and I'm going to take a look at the log file. So I'll deselect the checkpoint file, the log file, and since this was an optimization, I want to make sure that this box here, read intermediate geometries, is selected. And so I'm going to open that up, and you see that up here it's showing me that I had 6 optimization steps, and if you want to animate them, you can hit the green button. It goes very fast for 6 steps. Or you can cycle through them like this. If you want to do a side-by-side comparison, you can hit this button, and it allows you to look at all six structures in the job. We don't really need that for this particular analysis, so I'm going to go ahead and go back to this one. And what I want to look at, a couple things. First, I'm going to go to the Results tab and open up the optimization results. And what that's going to show me is information about the optimization. And so you can look at the total energy as a function of optimization step number. So this was the starting structure here, step 1. And then step 2, you can select it like this, or you can cycle through. And so you can see that there was a slight change in the geometry. And going from step 1 to step 2, the energy goes down. Step 3, hardly noticeable changes in the molecule itself, at least visually, but there were changes. And you can see that very quickly the optimization algorithm has found what it believes to be a minimum. And you can look at so this is the total energy versus optimization step, the root mean square gradient. So if you take the norm of the gradient with respect to each atom, or I should say this is the overall gradient here. If you calculate the force on each atom, what's the maximum force on each atom at each step in the optimization? So you see that the root mean squared of the gradient goes down to 0 at a minimum, or at a stationary point it should be a minimum, and so we're trying to minimize that. Likewise, because the forces on the atoms are related to the gradient of the energy, we see that the forces go down, converge to 0 This is the root mean square of all of the forces on the atoms. And then you can also look at the displacement. So when you go from step 1 to step 2, the atoms move. This represents the maximum displacement on any atom. You want that to go down to 0. Same thing here for the root mean square. So these are the convergence criteria that Gaussian is using to decide when the optimization algorithm should stop. And by selecting these different graphs, you can also save a picture, or you can save the data to a file, save the picture to your desktop, and then you can later incorporate that figure into your mini reports for whatever you're working on. And so that'll be useful for the optimization jobs, or for the report on the optimization unit of the course. And so here you're going to get information about that. What I wanted to point out next is that even though the Gaussian's algorithm had found what it believes to be a stationary state, it may not in fact be a minimum, which is why you want to do the frequency calculations. And so if we choose the last state, or the last structure in the list here, we can get the vibrational frequency information. Notice that this is in bold, and so we can choose that. But if you choose the first structure, since we didn't calculate the force constants at each optimization point, there's no vibrational information available for that one. So we want the last structure here. Open up the vibrations, and what we see here is that most of the vibrations, and you can cycle through them. Right? You can display them. Here we have sort of a bending mode in the amine group. If you go down here, you're going to be looking at this would be the nitrogen-hydrogen stretching, asymmetric stretching. Here we've got some symmetric stretching on the ring, all sorts of different stretching modes that you're going to find that contributes to the vibrational modes of the molecule. Here we're getting into the ring stretching modes, all sorts of different ways that the molecule is vibrating. What I want to draw your attention to is this negative frequency up at the top. And so what this indicates is that the structure that Gaussian has found here, while it may be a stationary point or close to a stationary point, it is not actually a minimum. This is probably a transition state of some sort. And so since we were looking for a minimum, this isn't what we want. And as you can see here, the fact that this negative frequency is detected for this type of motion, it tells you that the structure is not a minimum with respect to motion along this coordinate. Okay, so there's something wrong with this particular geometry in the sense that it isn't a minimum that we were looking for. So next, what I wanted to do was show you a couple of tricks that you can try to get from this non-minimum structure to a true minimum. Okay, so I'm going to close the vibrational analysis. First, I'm going to stop the animation. Then I can close it. And so what we're going to do is we're going to restart this job, and we're going to try to incorporate the vibrational frequencies that we've calculated into a new optimization using the same model chemistry, in hopes that this will eliminate the this negative frequency that we're seeing. So we're going to open up the calculation window. And so one thing you can do, go back to make sure that the opt frequency is specified. Now what we're going to do is we're going to modify some of these options here. So one thing that we can try to do is to incorporate a tighter convergence criterion. This will make Gaussian have to work a bit harder, in the sense that it'll need to do more steps in order to converge the molecule. And then the other thing that we can try to do is, since we have some frequencies on file for this molecule, what we're going to do is read the Cartesian force constants from the previous frequency job. So these are stored on the checkpoint file for this job. Now you've got a couple of options here. You can either overwrite the input file that you had previously created. That is, you can completely overwrite your past job, or you can create new files. if you want to save your original calculation and generate new files, what you want to do is go over here to the link 0 tab, okay, and then you want to change this old checkpoint file option to specify, and you'll see what it does is this is the original checkpoint file that we had created for our first job. Now, when we're ready to submit the new job, what we'll do is we'll submit and we'll save, but instead of using the original file name, maybe I'll put aniline1, something else. It doesn't really matter what it is. And then that's going to create a new input file and a new job, but the calculation will use the old checkpoint file to start this job. So we'll save, we'll go ahead and submit. We can close these. So it'll take just a little while to finish calculating. Okay, so you see that now there's a new checkpoint file, and here is the new log file. So I'm going to open that just like we did before. I'll go to the File Open options, make sure that Read Intermediate Geometry Optimizations is selected, and we'll open that up. Okay, so this time it did 8 steps, and we'll check the optimizations again. And so this point here, this was the last structure in our in our previous job. So this is the structure that we started the new calculation with. We see that we go one step and the energy goes up, right? That causes Gaussian then to go back the other direction, back to where it was essentially. And then the reason it took a few more steps is because Gaussian is now running under the tight convergence criterion. And so what we see has happened is that we know that this starting structure here, it's not quite correct with respect to the orientation of this amine group relative to the ring. And by reading in the force constants, Gaussian tried to get out of that, but because the energy went up so much, it came right back to where it was, and then we converged from there. So when we go back to check our vibrations, we're going to find that this approach that we took didn't quite get rid of that negative frequency. We're still stuck in that not a minimum structure. Okay, so that was our first approach to try to correct the error, and it didn't work, basically. Sometimes that will work, other times it doesn't. In this case, it didn't work. And so we need to take more, a different approach. So I'm going to stop the animation. Now, since there's something wrong with the orientation of this amine group relative to the ring, what we're going to do is we're going to manually displace the orientation. So I'm going to choose this torsion dihedral angle editor, and I'll select 1, 2, 3, 4 atoms. And now what I'm going to do is I'm just going to manually rotate it so that the structure's basically like that. Okay, and so I'm just going to approve that angle here. And what we'll do now is we're going to restart the job using this distortion, this distorted geometry. And we'll see what happens here. So we'll go to Calculate, Gaussian. I think we can keep the same option. So optimization frequency, we're going to go ahead and use the tight convergence criteria again. And we can still read in the Cartesian force constants for this molecule. It won't break anything. Again, if you want to create a new file to save the file, what we'll do is we'll specify and we'll make this old checkpoint file now the aniline1, right? So now we're using the second job that we've just done as the starting point for this, what will be the third job in the sequence. Okay, so we specify that. We can go ahead and hit Submit, Save, and now, continuing the sequence of notation, we'll use aniline2 for the third job. Go ahead and submit it. Close this. It won't take very long. Something's happening. It's obviously taking a little bit longer, so something good must be going on. All right, our job finished. So I'm going to go ahead and open up the log file. I see that that option is still checked, which is good. So I'm going to go ahead and open it. Look at that, we've got 41 steps now. So Gaussian had to do some work here to optimize the structure. We will look at the optimization. So this structure here, the first structure, this was the modification that we made. Then we see that in the second step, the energy went way up, and then Gaussian brought it back down, and then slowly but surely, the energy is getting lower and the forces are getting lower on the atoms and we're using the type convergence criterion, so it's taking a few steps here to satisfy those, but eventually we satisfy the criterion. We can go ahead and you could make images of this if you wanted to. We're going to go ahead and close it now, and we're going to check the vibrational frequencies on this last step to see if we have eliminated the negative frequency. Indeed, we see that we have. Okay, so now there's no longer any negative frequencies. That frequency that we were looking at is now positive. It's roughly the same magnitude, and you see that really for aniline, the minimum, at least for this model chemistry, the minimum energy structure has the amine group oriented in this fashion relative to the ring, rather than the other way, where it was more perpendicular. Okay, so what this example has highlighted is a technique to locate a minimum energy structure when you're having a bit of trouble optimizing the geometry, in the sense that you're having negative frequencies pop up in the final results. From here, now that we have a starting structure that is a minimum, at least at the semi-empirical level, and we've now figured out what orientation this group should have relative to the ring, now we're ready to set up perhaps a better calculation, that is a calculation, say, using DFT. For example, we might do our DFT calculation, use the APFD functional, and maybe we can start adding in bigger basis sets. Okay, and those calculations will take longer if you do an optimization, or maybe you just want to do, maybe you're fine with this PM6 geometry, maybe we just want to do a single point energy calculation. Here we'll go ahead and use our larger basis set, go ahead and add the diffuse functions, polarization functions that we want. So this will be an accurate energy calculation, so we'll just say this will be our final single point energy job for aniline. And so we'll use this particular calculation to analyze the charge density and things like that, the dipole moment, etc. So you can just save that. What I should have done here was gone here and specified. Well, we really don't even need to do this, actually, since we're not using those vibrational information anymore. We can just don't use the old checkpoint file. We're not reading anything in. We're just going to do a new single point energy calculation here. And so submit, save, and we'll call this aniline 3. Okay, now this one might take a little bit longer, more than a few minutes, so I'm going to go ahead and stop the video here.